Hello everybody, my name is Brian O'Sullivan. The paper I'm presenting today is called Sensor Tilt via Conic Sections. It concerns a specific aspect of camera calibration, namely misalignments between the lens elements of the camera and the CCD sensor plane. Listed above we have our simplifying assumptions, none of which are particularly true, but they allow us to build a working model from which we can progress to a more accurate calibration algorithm. So camera calibration is the process of determining the extrinsic, intrinsic, lens, and sensor tilt parameters of the camera. When these are known, distortions in an image due to the lens and tilted sensor can be modeled and removed. So here we see curved lines in the distorted image are straight in the rectilinear image. To the right of the frame is our camera model. We operate in camera-centric coordinates, meaning that the world origin and projection center are coincident, and the optical axis of the camera points along the negative z-axis. Here the world point P with a field angle theta is projected through the lens element to impact the CCD sensor at the point P. Camera calibration makes use of a calibration target, which is typically a 1 or 3 plane checkerboard, and the geometric properties are known. This matrix X is a list of the coordinates of the target corners expressed in the coordinate system of the target. So this brings us to the first map where we move from the registered coordinates X to the world coordinates P via the extrinsic matrix, which contains the rotation matrix R and translation vector T. So this tells us the position and orientation of the target when it is photographed by the camera. The next mapping is a nonlinear map from world coordinates to lens distorted coordinates P. Here are 4 of the fisheye lens models and the radial distortion curves below. These can be combined into a single equation using the Taylor series expansion, where the first 3 coefficients of each of these models is quoted above. So given a field angle theta and our azimuthal coordinate phi, we can write the lens distorted points in homogeneous camera coordinates as shown here. And this brings us now to the main result of the article, where we move from the lens distorted coordinates P to sensor tilt distorted coordinates P prime. Our schematic here shows our ideal sensor in green perpendicular to the optical axis and our tilted sensor in red. So for a given field angle, theta, we have a cone of possible light paths. This is intersected by the ideal center to create a circle of points P and our tilted sensor S1 to create this black ellipse of points here. So to find the coordinates of these points in the black ellipse, we look to this vector diagram and see that our ideal point P is scaled by a factor lambda to meet the S1 plane. So knowing that this vector Q in the local coordinate system of S1 can be written as a sum of minus Z plus lambda P, and taking it with the dot product of the normal to the tilted plane, we get our closed solution for the scale factor, which tells us where these points are. So now what we want to do is we want to rotate these black points to align with the coordinate system of S0. To do so, we use the Rodriguez rotation matrix. Our rotation axis is minus n cross z. To perform the rotation, we will shift our tilted plane to the world origin, as shown here, rotate, and then shift back. And this gives us the closed form of our tilt shifted map, moving from the blue points here to the green points. The final mapping is from our tilt distorted points to pixel coordinates, and this is the linear transformation where K is the camera matrix. To complete the picture, we require the inverse map, where we're going to shift from the tilt distorted points P prime back to P. So to do so, we will take this S0 plane, move to the coordinate center origin, as shown here. We perform an inverse rotation, as shown here, shift back, and then scale by division through the Z component. And this scaling is the pinhole projection, which gives us our tilt corrected map. So moving this green ellipse of points back to this blue circle of points here. So in conclusion, we have 2 new sets of equations derived from the conic sections, which we believe is of great interest for camera calibration and for computer vision in general. Thank you for your time and attention.